Hey guys, Mr. Betts here. Let's take a look at a few examples where we want to determine concavity and points of inflection of a function. So the first problem here, we're given a function and we want to determine where that function is concave up, concave down, and then the coordinates of any points of inflection. So in order to determine where a function's concave up and concave down, we're going to look at the second derivative. So I'm going to start this problem by taking the second derivative. And to do that, we first have to take the first derivative, and then we take the second derivative. And then to determine potential points of inflection, which is also where the concavity could change, we're going to figure out where this second derivative is either equal to 0 or undefined. So this is really similar to the critical values that we were finding on the first derivative, but instead of calling them critical values, now we're calling them potential inflection points. In order to solve this, by the way, the second derivative here is never going to be undefined. We can plug in any x value. So the only potential inflection points are going to be where this is equal to 0. We can factor out a 12x and we get x minus 2 left over. So we have potential inflection points at x equals 0 and x equals 2. So then to determine where the function is going to be concave up or concave down, I want to look at the sign of the second derivative. So I'm going to make a sign chart, and I'm going to include on the sign chart those points where the concavity could change. So again, these are the points where the second derivative is equal to 0 or undefined. And then we're just going to pick points on each interval and check each region. So if we plug in any negative number into the second derivative, and I'm going to look at this version of the second derivative because it's going to be easier to determine positive and negative. So any negative number, we're going to get a negative times a negative, which is going to give us a positive second derivative. So remember, when we're creating a sign chart for the second derivative, we want to plug into the second derivative. If we plug in 1, we're going to get a positive 12 times a negative 1. So a positive times a negative is going to give us a negative on that interval. And then any number greater than 2, we're going to have a positive times a positive, which is going to give us positive. So there's really 3 questions we have to answer here. The first is, where is the function concave up? So I'm going to say f is concave up. Notice that I'm saying f is concave up instead of saying f double prime is concave up. That would be kind of mixing language there, and we want to be careful we don't do that. So where the second derivative is positive, the function itself is concave up. So on the intervals negative infinity to 0 and 2 to infinity. F is concave down, where the second derivative is negative, and that's going to be on the interval from 0 to 2. And then the last question is, what are the coordinates of any points of inflection? Well, we're going to get points of inflection, remember, where the concavity changes. And we do have a change in concavity at both x equals 0 and x equals 2. So we do get inflection points at both of those x values. But we do want the coordinates because that's what it asks for in the question. A lot of times the question might just say determine the x coordinate of any points of inflection, and then we just would say 0 and 2. But we actually want to plug those into the function. So I'm going to do that off to the side here. F of 0 is going to be 0, and f of 2 is going to be, looks like 16 minus 4 times 8. So 16 minus 32 is negative 16. So we're going to say f has inflection points at 0, 0, and 2, negative 16. In the second example here, this one looks really similar, but we're starting with slightly different information. And this different information is key here. So instead of the function being x to the fourth minus 4x cubed, the derivative is x to the fourth minus 4x cubed. So a lot of times we're going to be given the derivative as a function, or maybe even the graph of the derivative. And based on that, we want to know where the function is concave up. So remember, concave up is where the second derivative is positive, concave down, second derivative negative, points of inflection where the concavity changes. So I'm going to start the same way I started the last one, by finding the second derivative. But this is just one step here. So to get the second derivative, we're just going to take the derivative of the derivative. And to determine potential points of inflection, we're going to set that equal to 0. I'm going to factor out a 4x squared, and what's left is going to be an x minus 3. So we have potential inflection points at x equals 0 and x equals 3. So same thing we did before, we're going to make a sign chart now, and that sign chart is going to be for the second derivative. And on that sign chart, I'm going to include the x coordinates of our potential inflection points. We're looking for the sign of the second derivative, so I'm plugging into the second derivative. But again, I'm going to plug into this version of the second derivative because that's going to make determining the sign a lot easier. So if I plug in any negative number, the x squared is always going to be positive. So we have a positive times x minus 3. If x is negative, that's going to be a negative. So positive times negative is negative. If we plug in a number between 0 and 3, say 1, we still have the x squared as positive. 1 minus 3 is negative, so it's still going to be negative. So it's important to understand that the concavity is not always going to change at our potential inflection points. We can see here that the concavity is down to the left and to the right of 0. Then to the right of 3, we plug in a big positive number. We get a positive times a positive, and that is going to be positive. So we want to answer the question now. First part of the question is, where is the function concave up? So f is concave up on any interval where the second derivative is positive. So that's going to be from 3 to infinity. Concave down. Now, this is going to be something that's a little different than what we saw with increasing and decreasing intervals. So we have this point right here at x equals 0 where the function, the second derivative is equal to 0. So at that point, the function itself is neither concave up nor concave down. So this is kind of a weird thing, but we are not going to include that point on the concave down interval because it does need to, for the function to be concave down at the point, it has to have a negative derivative at that point. So we're going to list this as two separate intervals. So on the intervals from negative infinity to 0 and from 0 to 3. So notice we're excluding 0 because it is not concave down at 0 because the second derivative is not negative at 0. Last question is coordinates of any points of inflection. This graph is only going to have, the graph of f is only going to have one point of inflection at x equals 3. So f has a point of inflection at, and it's going to be 3 comma, and then we need to figure out what the y coordinate is, and it's actually not possible to determine the y coordinate, and the reason is we don't know what f is. So we can't figure out what the value of f is without knowing what f is, and even knowing what the derivative is, it's not possible with the information given to us to work backwards and figure out what f is. And it turns out that there's lots of different functions that have a derivative of x to the fourth minus 4x cubed. So I can't answer the question as it's asked. It says the coordinates of any points of inflection. So let's change the question here a little bit just so we can answer it. And we'll just say the x coordinate of any points of inflection. So f has a point of inflection at x equals 3. All right, the last one, the function looks hopefully familiar, except this time now it's given to us as the second derivative. So in the first two examples, we started by taking the second derivative. This time we're given the second derivative. So all we have to do to start this is to set that second derivative equal to 0, and then solve that for potential inflection points. So we can factor out an x cubed this time, and what's left is x minus 4. So we have potential inflection points at x equals 0 and x equals 4. And then we are going to use that to make our sign chart. And plugging into the second derivative, but I'm going to plug it into that factored form. Any negative number to the third power is also negative, and then a negative minus 4 is negative, so we have a negative times a negative is positive here. Between 0 and 4, I'll plug in 2. 2 cubed is positive. 2 minus 4 is negative 2, so we have positive times negative is negative. And then a number bigger than 4 is going to give us a positive times positive, which is positive. So based on this sign chart here, we are going to say that f is concave up on the intervals where the second derivative is positive. So that's going to be from negative infinity to 0 and from 4 to infinity. F is concave down on the interval where the second derivative is negative. That's going to be 0 to 4. And then the last part, this is the same problem we had in the last example. If we want to know the coordinates of any points of inflection, we can't answer that because we don't know what f of x is. So all we can answer here is the x coordinates of any points of inflection. And f has 2 points of inflection because the concavity is changing at both 0 and 4. So f has points of inflection at x equals 0 and x equals 4. Now, real quick, before we wrap this up, I want to point out a couple of things about the sign chart. Some things that might help make the sign charts a little bit more quickly, and this works whether it's a sign chart for the first derivative or second derivative, doesn't really matter what it's for. If we have a factored form that we're plugging in for a sign chart, notice that if I go back to the first one here, we had a single root at x equals 0 and a single root at x equals 2, and at those single roots we had sign changes. On the second one, where we didn't have a sign change at x equals 0, it was a double root. So anytime we have a double root or 4 roots or 6 roots at the same point, we are not going to see a sign change. Anywhere we have an odd number of roots, we are going to see a sign change. So knowing how many roots we have at each of these zeros for the second derivative can help us make that sign chart. If we know the sign on one interval and we know if the sign is either going to change or flip, that can make it go really fast without actually having to choose numbers on each interval. It's a shortcut that you can use if you want, if you're comfortable with it, and if you're not, then you don't need to.